Hello hackers, welcome back to another programming session. Today we are going to write some programs in x64-bit Linux assembly, and we'll be developing our own shell code from the source code of the assembly that we are going to write. So let's dive straight into our programming part, and I have prepared some basic slides for this one. If you are not aware about what assembly is, I know you are. But just for your information, it's a low-level programming language that is closely related to the machine code, and if you ask me the other part, it is a human-readable, close-to-machine programming language. So, and it's very architecture-specific. So the benefit of that one is you can write hardware-specific instructions that performs well compared to other programming languages. And this is the structure of. These are the available registers in 64-bit assembly, and even though 64-bit, still we can make use of other areas like 32-bit, 16-bit, or 8-bit upper and low bits. It totally depends upon your requirement. It doesn't need to be the entire 64-bit. You have to utilize every time. But if your instruction is just needs only 8 bits, always try to make use of the lower bits, because that's how we are going to optimize our code for shell coding. I will show you how to do that in upcoming programs. And these are the other, this is the same kind of register list, but here you should be aware about the stack pointers. It's nothing but 8 points to the top of the stack always, every time. Whatever operations we do, push or pop in the stack pointer will change according to that. And RIP is another instruction point. It's very important for when we are trying to develop your own exploits, because hijacking this RIP will help you to redirect the programming execution to your exploit that you developed. So that's basics of the registers. This is the main important part here. From the basics part, each sections is very important. You should be aware about these sections. Data section is basically for initializing variables. Initialized variables, and BSS normally is for uninitialized variables like arrays and something like this, those kind of stuff. Mostly is basic. It is used for arrays areas, and it has different instructions for that. Normally the instruction that is start with res, you see more on this BSS areas. And text is the most important part. Here we write instructions that is going to be executed by the program, and you can label something, and under the label you can write your instructions. That's very helpful by organizing your code. And we do all these things on the upcoming programming sessions, so it will be clear for you. So what else? These are the other data types that is available. DB, defined bytes. If you want to do higher bits, then DW, and when you need 16 bits of data, like that, you can choose your own data types. And as I said, res is a reserve keyword, and it could be added with all these available data types according to your needs. So these are some other basics. When you say move RX to RBX, it means we are moving the value from RBX to RX. So after this, RX will having the value of RBX. Then when you say in square bracket with move, it says RX will contain the value stored in memory at the address contained in RBX. So suppose RBX will have a memory location. When you do this operation after that, RX is going to have the value that is stored the memory location of RBX. That's a major difference between normal move and the square bracket move. It's basically nothing but it's just referencing the memory. The same thing you should be knowing is the difference between this and LEA, as we already checked. This operation will be referencing the value referenced by this memory, but this operation actually directly loading RX with the memory location itself, not the value. That's a major difference you should be aware of, because we will be using this most of the time. And regarding the stack, as you know, normally when you write a normal program, your function, when you declare some local variables, is going to be in the stack, and you know how the stack is created. So the stack is in a last in first out manner. So normally the function pointers, function parameters are pushed into the stack. So when we are pushing into the stack, this is happen normally. Basically it pushes the base pointer to the stack. Then the RSP, means the top of the stack, is set as the base pointer. Then it allocates the space for the stack using the subtraction, because the stack is growing down, it's not going up, in fact. Then do all the operation. Then we take it back, set it back, the RSP with the base pointer. Then we save the RBP, like we are taking the RBP from the stack and place it back to the RBP itself. So this is where we preserve the values when we do some function calls. And this, if you ever reverse engineered any of the programs, you could see this kind of patterns. I mean, there are more instructions definitely, but this is commonly the that you see. Okay, what is next? Yeah, this is the way we declare. You have to define your variable name, then the type, then the value. Value could be in hexadecimal format or string. Directly you can store it in string. And the main important part when you're declaring it using hexadecimal is you should be knowing the byte order, because you have to save it in Little Endian format. So Little Endian is nothing but it's a reversed byte order of any string that you normally use. We will do that in our programming, so it will be clear for you. So that's some important things. Yeah, we will be doing some GDB stuff, so I will explain all these things there. And this is we will be using NASM assembler for our programming, and this is a command to convert your assembler. You convert your assembly code using NASM to object code. Then we will be using a linker, so that linker is going to convert to the exact binary, targeted binary. And another thing you should be knowing is the order of the system calls when you are trying to call some function call. This is a function system call. This is a way you have to place the rest values. The RX might be we should be having system call number. Then the second is a second argument. Usually this is going to be a second argument for the entire instruction, but this is a first argument for the function. So RDA should be having the first argument, then RSA, then RDX, then R10, R8 and R9. This is, when I'm going to write the program, it will be more clear for you. So the important thing here you should note is when you are after the function call, suppose the function is returning something, the return value is going to be stored again in RX. So RX will be replaced at that time, only if you have a return value from the function. So that's it. These are related to the shell codes. We will come to that later. So let's dive into our first program that will be clear for you. So I'm going to use the available, the built-in available IDE for this one. I tried to record this video using the Codium, but Codium did eat up my Linux memory, and it completely got stuck because of some plugin updates and reasons. So here, let me start by writing our first program. Let be write hello .asm. Stored there. Yeah. So as I said, we have to mention our sections. Here the section is going to be initialize data. I'm going to initialize, imagine it's going to be a variable called text, and then I'm just defining it as db defined by bytes. So I'm saying hello hackers. You can either null terminate using 0, or if you want a new line, you can do this like this. So the next thing is either you can manually so here should be the next one. Either you can manually check the number of characters, or you can automatically calculate using the EQU operator, and this will be this is a way, actually this is a really weird way. Then you just mentioned your variable name, so basically the len will have the number of characters in the hello hacker string. That's what it means. Then we define our instruction, the main code instructions, and we have to mention it's global and start. If you try to reverse some C programming, you may see this as global main instead of global start, because it's a raw assembly. It is accepting the global underscore start. So this is a way it is structured, and way it is how it works. So now we define our start. So here it starts with the actual assembly programming. So we have to write something to the console. For that, what we can do is we can check the parameters for write. You see there's a file descriptor and a pointer to buffer or the buffer reference, then the number of I think the size of the buffer. So basically we have to refer to this buffer memory and then specify the number of bytes to print. That's it. So before that, you should be knowing the syscalls for this one. For that, what you can do is see, if you check this one, if you are not aware about the the file descriptor definitions, you can go here and check the file descriptors, and there are different numbers: 0 for input and 1 for output and 2 for error. So we are going to make use of this one because we are going to use, when you check this one right, the first parameter for the write was the file descriptor, and we are going to make use of the standard output file descriptor because we have to write to the console. So that's, and then now we have to find out the system call for this one. For that, you can, again, it is Linux, so everything is available inside here itself, so you don't need to go somewhere else to check. See here, you can see the right system call number is 1. So now we have everything, the function name, the parameters, and syscall number. Start our programming. You have to move, the first instruction is RIX should be filled with the syscall number 1. Then the second parameter RDI should be again the file descriptor 1, write to console. Then the third is not going to be a move, instead we are going to point to the buffer that we have to write. So LEA is going to be we are going to load the memory location of the variable txt to the third argument. So RSA is going to have txt. Now we have the syscall number, the file descriptor, the reference to our memory location to print. The next instruction for RDX. RDX is the next register we have to make use for system call. It should be having the length of the buffer that we need to write. Then we do the syscall and say it's right, and the semicolon is for commenting. Let's build it, and then some hyphen of just say write exe write some instruction not supplied in 32 or error instruction not support. What was that? RX move RDX. What was that? Error, it's instruction not supported in 32-bit mode. Why this is not supported in 32-bit mode? Which instruction 11? Why move is correct? MOV RSI RDX. Which instruction? I don't know. Let me check it again. Instruction not supported in 32-bit mode. Why it is going to console? Okay. Oh no, it's my mistake. Because here you have to mention 64 exclusively, because if you don't mention, yeah, it goes to 32-bit. Definitely 32-bit doesn't have RX registers. That's why it's okay. Now it is fine. We have an object. Now we have to link this object and create a binary. Okay, before that, let me move write exe write object file, otherwise you will get confused on that. So ld-o write obj file, and then say this is actually a write, say bin as okay, write underscore elf or exe, whatever it is. No, what was again the command? What was the command for that one? Source. Oh no, is it because of that? Okay, write obj. Alright. Oh no, I did mistake. Right. Oh, right. Oh, you didn't create the file. Let me check it. Oh, it didn't. Okay, let me create it again. Right. obj. So it is, yeah, right, obj is there. Now we link it. Link it and say the output is right elf. Oh shit. Should be, yeah. Now if you write if you run the program, you get hello case. Okay, segmentation fault. Why? Because we didn't exit this instruction application gracefully, because we didn't have, because it's a raw assembly program. You should write everything what you need to achieve. So you definitely have to call the exit for that. And if you check the exit is called is 60 and okay, yeah. If you check the function for that one has only one parameter, that's just the status. So it normally the status it's a recent code, so you can pass it as 0. That doesn't matter. So just do that syscall rx and it's 60 move RDI, reason is 0, again syscall, it's going to be exit. Save it, try to run it again. it should be working fine now. See, it just printed without any issues because we now have a fully functional assembly program. So, but this is a good assembly program, but never think that, don't be in a fascinated world that this is an optimized program. I will show you why. Suppose if you want to try to develop some shell code from this one, you will be in trouble. I'll show you why. So let me show you the shell code behind this. objdump -m indel -p. What is right underscore elf. See, and this is called the B8001000. This is called shell codes, and these raw bytes are going to be directly executed by the processor. So, but the issue here is you can see hell lot of null values. All these zeros are considered as nulls when you try to write shell codes. So if you ever use MSF Venom or any other programs like that, we normally try to avoid, we supply, when you try to generate shell code from MSF Venom, we supply bad characters to be avoided. Normally it's definitely it's null. Then there are some other bad characters, but when you write manual assembly programming, you don't create that much of bad characters by intention, but maybe high chance like this, because we didn't utilize registers properly here. There are so many ways to avoid this. We'll start with the first way. So the first way always is instead of using the entire 64-bit register, you can make use of the lowest register here. Instead of RAX, you can use AL, and for RDI, instead of that, you can use. Let me check it. I forgot that. Normally, RDI, yeah, it's DL, and as is fine. Again, RDX. What was the lowest register for RDX is DL. We can make use of DL. Again here the same thing, L, RDI instead of RDI, DL. Try this one and let us see the shell code. No. Let's confirm it is working. Yeah, it is working. And what about the shell code? See, now if you compare this shell code, actually we were seeing a lot of nulls here. See, now we completely avoided those zeros here, but still we have some zeros here. This is because I think this is because of null terminator, and here you see this one again some zero because it's an exit syscall. So but for the write syscall, we eliminated most of the zeros, null values, but still we see something here. So there's another way of optimizing this one. So just imagine here we need a reference. So just RSA needs a reference to the memory location of the text. So instead of using this LEA here directly, we can try just imagine, okay, just comment out this one, and this one. So Now what we do here, instead of saving this variable separately, we are going to push the strings directly to the stack. So what happens after that? So when you are pushing things directly to the stack, you should be knowing some rules. Like when you are pushing something, it's a 64-bit register, so we have to divide it by using 8 bytes. So basically a character is 1 byte, so we can divide the string using just count it like 1 2 3 4 5 6 7 8. Yeah, you can divide the entire string like this. One string hello, then space ha, then the remaining string. Divide the string and pushes it to stack. And when you're pushing that to stack, keep in mind that you should follow the little endian format. You should be in a reverse byte order, not the way exactly that we see here. So what we can do here, we try to we are going to create a stack first. So, and as you say, when you say the stack, actually I'll draw this here, then it will be clear for you. Duplicate slide. Here what is going to happen is insert ascend table. Yeah, okay, let this be the string. We are going to create a stack like this here. Here is going to be the null terminator. Then here is going to be the second part of the, maybe I think hackers or something. So this will be having the second part of the string, and this is going to the first part of the string. This is going to be the stack that we are going to create. We have to push these strings into a stack like this. Then we hear that the RSP, the top of the stack will have the RSP pointer. RSP is going to point to the hello HA, the first string. Then we refer the stack, and we will say how many characters we need to print from the stack. That's another way we are going to print it. So let's go back to the program and what we are going to achieve here. So I'm going to rx XOR first and push the rx to the stack. So when you're pushing a 0 kind of thing to the stack memory, it is going to be considered as a null terminator for the string. That you should be keep in mind. That's why we do push the first string. Then before pushing the second string, we have to convert this to the reverse byte order. So I'm going to use 2 3 4 5 6 7 8. I think this is the easiest way to do this. Dot encode. I'm not sure. I forgot this again. Oh yeah, it works. Oh, you have to do the other string also. CKRS. You can say that if you want, you can say the new line. So we already push the first string, the null terminator. The next is I'm going to use of another, okay, just for any register you can make use of. I'm going to use RBX, and why I'm going to use RBX is I just clear the RBX and push move RBX with this value. It's a reverse byte order of the second part of the string. Then again I'm going to use the same register. I'm not going to confuse you with more registers. Again, I'm cleared the register and I came here and I did take this one. This is the first part of the string. So now we have just like this null terminator here, and the second part here, and the first part here. Now the RSP is pointing to the top of the stack here. Hello, hello and HA, the first string. So we have to push the RBX. Now we push the RBX here. Now I say I'm just doing the same syscall, move RDL, same thing. Instead of this one, I'm going to use the move instruction here because I have the direct memory here. The RSP is pointing to the top of the stack. So RSP is going to have a memory location that is going to be the top of the stack. So I'm just moving that RSI to RSP to RSI. Then rest is we don't need. There's no len here, so we may need to specify the number of characters. It was 8, 9, 10, 11, 12, 13, 14, 15. I think including the new line it is going to be 16. So that's it. So I'm trying to avoid the null references from this right syscall because exit already have a 0 there. So normally we are not going to use exit syscalls in our shell coding, security related coding. So I'm trying to avoid the right syscall null characters here. So we did it in a different way, like instead of creating a variable, we directly push the values to the stack. For that, we just XOR the RX and push the null terminator to the stack, then the second part of the string to the stack, and again we clear the same register and use only one register here, RBX, as an extra register. Then all the all the other things are there. The main difference here is this one. Instead of LEA RSI with the TXT register previously we replaced that with the the top of the stack RSP. RSP is now pointing to the last string that we pushed the stack, that is hello HA. So if everything goes well, this should be printing the same thing. Just writing adapt. Let's try. Actually, it is not printing the entire stack. I think it's not printing the second one. So come here. We XORed RBX and we moved the second part of the string. Then we again XORed RBX. Again push back the new value here. Then here what we do, what could be gone wrong is we have the first string here, push. Oh no, we missed one push here. Yeah, we didn't push the first second value RBX. See, we pushed the null value here and we did RBX with the second string, but we missed the push. We didn't push the second string to the stack. That's why we didn't see the second string. be working now. See, it works perfectly. So what's the difference here? Why we are trying in this way is we are trying to avoid the null characters from the write function. So if we try objdump -b our write underscore elf, see, we completely avoided the null strings. I don't see any null characters, so null bytes here. Here, see, there's no zeros, no zeros here. So here, the only null you see is exit syscall. Apart from that, everything works perfectly here. So this is a way we can optimize. We can write the write hello world or hello case in a normal way just by declaring a variable. That's what everyone is showing when you check assembly programming. But here there is some other thing, like even though it is optimized, the number of instructions are really high here. That's another case, and the shellcode is normally depends upon the space that you are going to get in an exploit. Like when you find an exploit or when you find a space, it normally is called code cave in an application. You can inject your own shellcode inside that. For when you find a code cave, that actually that depends upon the shellcode should be dependable on that. If the shellcode is should be instruction set should be less, or the space that you are getting inside the code cave is less, then you have to develop your shellcode based on that. Even though this is optimized, the number of instructions are really high, but it is far better than the other way, but not good for a beginner. But try to practice it using different ways. Like it's easy to write that hello hackers print console normal way, but when you are focusing on shell coding, yeah, definitely should be focusing this kind of stuff. So that's first part of this one. Now we move to the next thing, what to say, the shell, the actual shell. Now we have a write to the shell. Next we are going to get a shell from the assembly itself. That means we are spawning a shell. It's just calling an exec v inside the assembly. That's it. It's nothing complicated. So now you know the basics and how to avoid, how to make proper instructions, how to get rid of your nulls. And I always recommend to use XOR first before you try to make some 64-bit movement on your registers. So now let us create another program. Let's start. Just say it's oh no, where it's gone. It's going to be like SPN shell.s. So here we can make use of the same thing. I start with the traditional way of doing it. Dot section data shell db is going to be bin sh or bin bash, or you just try to. Here we don't need any new line because we're not trying to print out anything to the console. Then start dot text underscore start. Then oops. So here we have to do the instruction set. as I said, we have to make use of the let us say which is called exactly is called. So you can check man to xv. See here it is pointed to the path, and the second and third arguments are nullable. You don't need to worry about that. But if your program has command line arguments, you may need to use the second, and if the program is going to use any environment related parameters, you have to use that. But here in our case, we don't need anything like that. We just want to execute the shell. So this is a parameter path name, then the second and third are null is fine for us. So that's very simple. So what exactly we need next is the syscall for this one. Exactly, yeah, syscall number for that one is 59. So let's start. Move rx with 59. Move RDI. Okay, I is not move. We can use LEA RDI with the reference of SHLL. Then move RSI null. Again, okay, the better way of instead of moving 0 to there, better way is XOR RSI, and the third parameter also nullable, so we don't need to pass that. RDX null, RDX syscall. So this syscall should be working for the shell. Spawn a shell. So that's it for, if this works well, actually that's it for this what say the spawning a shell. So let us go and find I'm going to say shell obj and what was the name of the file? Spawn shell. Label alone online with a colon. Okay, what is that? Section data, section text. Then what is that? Yeah, sometimes I get stuck. What is this? Is this section text? Oh, which was the line number? 555. Oops, I missed the main thing. Global. Yeah. Oh, that is another thing. So yeah, that's it. We did this, and this it's better to make mistakes and learn it, because yeah, the syntax you should be familiar most of the time if you miss something, because I'm continuously switching from Rust in between Rust and assembly. Yeah, the syntax, keeping the syntax in my brain is really okay. Whatever it is, we now have this one, so we going to do ld -o write okay, not write shell exe, and what was it, shell make it from, what was that syntax for that, I forgot. Oh sorry, syntax is like shell obj, then you say shell exe here. say shell exe is going to work. Shell exe. Oh yeah, see, you got another shell. Like, you can see the difference here. This was prompt that we ran the shell, and when we ran this shell exe, we got another shell. Yeah, it works perfectly. So now the next thing is how to develop our shell code, and how to I have C wrapper, and even I do have a REST wrapper. If I do with the REST, it may take more time. So I'm going to create a shellcode that's going to be inserted into the C wrapper, and we see how we can run the shellcode inside the wrapper and we get the same result. But before that, we have to analyze the shellcode, or objdump -m intel, then we say -d, or what was the exe name? Shell exe. Yeah, see, you can see a lot of nulls in between here. See, a lot of nulls here. Even though we use RIX, actually it is optimized internally with using EAX, because the value that we are pushing is very just needs only, even EAX is not needed. You can directly push to the AL. So what if we move AL, and one more thing here you have to notice is that we have the number of characters here. See, 1, 2, 3, 4, 5, 6, 7. Only 7 are here. So definitely it's going to be parallel with the null character after this. So let's try optimizing one by one. We tried this one, XORing. So this AL59 move will be replacing these null characters, and I hope, but I'm not sure about the other one. Let's try. Okay, then maybe XORDI before this may reduce. Let's try that. This one. Let us see, it is working. Yeah, it is working. So objdump intel -d shell exe. Oh yeah, but we couldn't replace this string, but we remove the nulls from here. So see, we remove the nulls from here, but we still have some nulls here in these instruction sets. So what if we use the same approach we did for the other one, the normal string, pushing this to the stack and reference from there. So we try that here, same technique here. But before that, as I already mentioned, it should be pushing the string in reverse byte order. So let us say this one in reverse and encode hex. Yeah, this reverse byte order may help. So we have only one string here, so it is easy. What I'm going to do is XOR RX, just like that previously we did. Then push that to stack. Now we have the null character pushed. Then we are going to make use of another register rdx, and move rbx with our reverse byte order string. Then we push that string to stack. Now you know how the stack works, right? We did that for the previous one. And now we do this, and instead of this one, move RDI. Instead of LEA, we are going to use RDI with the RSP. So RSP is going to be pointed here. So the remaining syscall instructions are same. Let us find how it works. We did create Shell.exe. Just check it is working or not. Works perfectly. So let's try to try our shellcode. Oh, see here you can see a lot of stuffs removed. We had some nulls here. We removed that, and the only null here is this one. This is after the string, I think. This is because as I said, we didn't fill up the 64-bit register exactly with the number of characters required. That's why again you're seeing this one here. So for that, what we can do is we try to add one more character. We are just going to fill it, and if you know this one, by adding a slash doesn't make any difference inside the Linux, because it's a POSIX rule that even if it's going to be on the path, if it's going to be double slashes, it's going to be considered a single slash. So just try that, and we got this in. So now the number of 8 character rule is done. So we are not allowing the assembler to fill it with or to pad it with null. So let's try that now, and once we have that one here, let's try to do this again. This one, and this is here. Let's try to run it first to ensure this is running. Yeah, this is running fine. So let's try to get the shellcode. See, now we avoided all the nulls from here. See, now we have the complete shellcode without any nulls. So this instructions, see, this shellcode could be used inside anywhere, but just because we are using the pushing to stack method, it is kind of position independent shellcode, so you can try it in a wrapper. So now we have to get this shellcode directly. You have to extract this in C format. For that, I can check with the command line foo site for getting the shellcode commands. I copied the actual command from there, and what I experienced was there were 2 commands, and one was this one, and if you try to use this one, you may not get all the shellcodes. One part was missing, but the second one I tried was this one. So this one was working perfectly for me. So try to make use of this one. Now we see the shellcode, but we need to extract it in our own format. So what we going to do is shell.exe. Oh yeah, we got it. I think yeah, let us test it inside our another one. Oh, sorry. File open. Oops. What is it? File open. And I have a wrapper here. This is nothing but we allocate some memory and try to just set it as executable, then run it. gcc-o test shell and run this. Oh yeah, it did. So if this shell code is correct, you will get the exact result that when we are running the separate running the shell assembly generated binary. So just try this test shell. Oh yeah, see, we got it. Just 35 bytes of shell codes, we got a shell. So this shell code is working. This is how we extract shell code from our own assembly program. Hope you got the basics of this one. This is really interesting programming. Like, I really enjoyed this assembly programming. Initially when you look into this one, it may be very confusing since even still I'm just learning, but it's really interesting one. So now we have our shell code running for shell. So now the biggest challenge is developing a shell code for the reverse shell. For that, before moving to that, you just ensure you got all these things that we did. If you have some doubts, I strongly recommend to post the video and refer the sessions where you got lost. Now we are moving into the biggest challenge of the reverse shell. Reverse shell for first we had to develop a reverse shell in assembly, then we had to get the shell code. Even before that, the best way for that one is I have a reference file that is a reverse shell.c file. So we will be converting that to assembly. That will be the easiest way, I can say. So let us start. Just as I mentioned, if you got stuck on somewhere, just please post the video here and learn all about the optimization and shellcode development before what we covered, then continue this. So now we have to move to the next one, that is going to be the shell asm. Okay, let's save that and open the reverse shell file. This is a reference file we are going to make use of, and here we have multiple syscalls. Like first syscall is for socket, and the second is a connect syscall, and third is a dupe or no, dupe we have to call 3 times. Dupe 2 is three times. One is for stdin, and another one is for out, another one is for error, and the last one is for execv that we already did. We know how this works, so it will be easy for this part will be easy for us. So we have to make develop assembly for these things. So before going into that, definitely you should know the socket syscall number, how the function works, then the connect syscall number and dupe syscall number. So first thing, you should be knowing how these things work. Like when you call a socket, the first thing you are passing is af underscore inet and socket string. So there are numbers for this one. You should be knowing these numbers because we are writing raw assembly programming. So you should be knowing these numbers. And third argument is 0, that is fine. And here is a catching point. The beginning of before we started the programming, I already mentioned when we call as when we try to call a syscall, I mean, like when you're trying to do a syscall, you have to place the rx with the syscall number. But if your function is going to return return some values, your syscall number will be replaced with the return value of the function. Here that is happening. Here we have a socket file descriptor, and if you check, that socket file descriptor is used on the connect and all other syscalls. So you should save this socket file descriptor for future references when you get it back. So yeah, let us try to do that. So it will be easy for us to do that. And one more thing, yeah, here we are going to apply all the things, and you should know the basics of programming here, because when you say this variable, I mean this structure, something when you define here, this structure is actually getting allocated in the stack. So you have to do the exact same thing when you are trying to write your assembly programming. You have to create this this structure in stack, then yeah, you just do the reference. And some other things you should note is the reverse byte. You have to keep in mind the reverse byte order. All for this, I mean, just because it's little endian format, internally the final binary will have the reverse byte order for this one. That's very important for our shellcode. So let's start just converting this one. If you check the socket syscall number, you exit socket syscall is 41, and what is the connect? Connect is 42, and what was the dupe to? Dupe to syscall is 33, and exec we know, we already did that, so we can make use of the same assembly instructions we did on the previous one. So for this one, we have to create these three things. I mean, 4 syscalls. No, 3 syscalls: 41, 42, and 33. So let's start our visual assembly. The first we are going to make use of. Before that, you should be knowing the AFNet definition. For that, the best option is Elixir Bootlin. You can check directly inside the Linux itself, but yeah, this is the thing I reference. I started using when I started working on eBBF, so this is very helpful. And see, AFNet has a value of 2. What was the other one we need? We need soak stream. Soak stream should be, oh no, that is not 1, but I think value is same. Let me check. Yeah, is 1. AFNet is 2, soak stream is 1. 2, 1. Anything else we need? Yeah, I think that's it. So let us start our code. First we have to say section underscore start. We will be making use of we are not going to make use of any like not section underscore start, section txt global. That was something that I missed on the last program. Global start underscore start. So yeah, here we are going to directly create the assembly. So the first thing is you have to create the syscall for socket call. For that, so here we are going to make use of the optimized way of, so before doing any operation I prefer to clear the registers, so definitely more clearing RX will be good. Then we move the L is 41, right? I did write the syscall number here. Yeah, socket syscall number was 41, and we did check it here. 41, 53 and 42 I'm sorry, 41, 42 and 33. 33 is the last one for this one. Yeah, where is that? So the syscall number, we place the syscall number. Now we need is the second parameter AFNet and sock stream and one more 0. So the second parameter is going to be RDI. So I'm just clearing the RDI here and move instead of the ended RDI I'm going to use it's going to be AFNet, right? AFNet is 2 that we already found. So the third parameter here is going to be RSI. So I'm just clearing the RSI and move the RSI, lowest bit of RSI with what is the sock stream is 1. Sock stream is 1. Now RDX, RX, RDI, RSI and RDX is the next one. So I'm just clearing RDX, move okay, no, we don't need to do any move here because I think the third parameter is already 0. So yeah, just keep it like that. So we have the socket parameters made, syscall number with all the parameters. First parameter syscall number, second is RDA has value 2, AFNet, then sock stream has 1, then the third RDX has 0. Now we do the syscall. Socket call. So here's a cache. Just because you have to remain this keep in your mind. We already made a syscall, and the syscall has a return value. So the RX will be having the syscall, socket file descriptor. So you have to keep that RX somewhere, because if you are not going to keep it for making other syscalls, we have to replace the RX with the new syscall numbers. So definitely you have to keep that one. So the best way, what I see is here, if you see for the second connect syscall, the first argument for that one is the reference that is we got from here. So the logical way of doing that one will be like move RDI with the RX value. Here we are preserving the socket reference, socket file descriptor, reference for future use. So we just kept it inside the RDI because if you keep it RDI, we don't need to mention, we don't need to fill the RDI with every time with the file descriptor. Here we are going to make use of RDI for first argument for so many functions after this, so it will be easier for us. Now we have our file descriptor kept on RDI, so we don't need to fill it every time. So next is the connecting the connection syscall is very important here, because we are going to use the same rule that we use for optimizing the string, the write or shell that we did. We are creating this structure in stack, and we are going to refer that stack address here. The first one is connect syscall is syscall file descriptor for socket that we already have. Second, it needs a reference to this socket address, so we have to prepare this in the stack, and we have to refer that here. And keep in mind, when you are preparing the stack, we are going to create in a reverse order. First we are going to push this, then this, then this, then we say the reference. As you know, we already explained that, so I'm not going to explain it again and again, but you have to keep other thing. This should be in reverse byte order. And what else? Yeah, where is it? So the first thing we have to push is the IP address. So for pushing the IP address to the stack, you can make use of any register here, so you don't need to worry about that. But let me do. I have to convert this. Okay, this IP is basically my machine IP. I'm just using this one. I'm going to test the reverse shell here itself. So this IP should be converted to the reverse byte order. So let me try this one. I have a Python program here. What is that? The Python program for that one was IP hex. Oh, sorry. Python IP hex. Then the first parameter is this one. This is just give me, I mean, you can try, there are so many online services you can make use of, so you can try that if you want to use. So just take that and push that to the stack. So before pushing, what I'm just recommending is just RCX. I'm going to make use of RCX or RDX. Okay, RB. Okay, I'm just going to make any register you can make use of for this one. XOR RBX, clearing the stack, move RBX with this one. So yeah, if you want, you can make use like caps. That's the usual way you see in every program. It's the same thing. It's a reverse byte order of the IP. I will comment it here. So little Indian, okay, little Indian of 192.168.1.199. Now I'm pushing this to the stack, pushing RDX to the stack. Now what was next thing? Where is that? Now you see we have okay, before that, okay, I forgot one thing. When you check the connect syscall, see the connect syscall has a size of this one. For finding this size, either you can directly run this program and find out printing it out, but if you check this go deeper into socket programming, you can find that the size of this one is 16. And apart from this, there's another field in this one that is actually not necessary. It's not mandatory for setting it up, but it is used for padding the 16 bytes. But don't go blindly with the 16 the size of this one. You can try yourself by creating, just say gcc -o c shell, then rev.c. So let me see the C shell. strace could be used to find out the details of this one. You have to run this. So if you do an strace and using the -f, you can mention which syscalls you want to extract, filter it out, so it will filter out only those. I didn't do that here, I just messed up, so but it is somewhere here. You can see, yeah, here you can see the syscall is making. Here, see here it is making a syscall, a socket call, then connecting. See the reference is getting back is 3 and is using the 3 here everywhere. So we are dynamically doing inside our assembly, and see it's passing here, then AFNet, then the port, then the address as a structure, then see the structure is formed in this way, like first is checking the AFNet, then the port, then the address. That's why we push the address first in the stack, because the next thing we need to push is the port, then the final push should be the AFNet. As a reverse, I mean, I already explained. So see here you can see the size of the structure is going to be 16. Either you can find it this way, or you can directly print it in your C program and try to find it out. And if you go deeper into socket programming, you know all the other fields of this one, how it is constructed. And that's our next major thing that we are going to do here. Till now we were using only push instruction, but now we are going to make use of the next thing we need to push is the port and then the family. So for this one here, after pushing this one, you're going to make use of a word called push word, because it's not a normal thing, it's a 2 bytes, like it's a word. Data type is not the normal one. So because when you're pushing a normal value, it should be between 0 to 255, you can directly push it. But when it comes to a word like a 16 byte, so just it is bigger than a normal byte value, so just consider that. And here we are doing the same thing. We are going to push this one in reverse byte order. You can try getting this one online or whatever it is. I already calculated this one. The normal way it is, it comes is I mean, it's a reverse order of this one. It's 115C, but we have to use 5C11. That's the difference. You check anywhere, you can just use a calculator and find it out. It's easy. You have to push this one to the stack and come to this port 4444. You can use any kind of port. Try to do some other ports in reverse byte order and try this one. Now we have and if you check here, it is having the AFNet first, then the port, then the IP. Now we push the IP and the I mean, like the port number. Now we have to push this thing to, I mean, like the AFNet to this one. Why we are using word here is, like, if you check the structure of the socket addr_in, you know how it is arranged. Actually, it's not normal. It's not like a normal push for this one, normal move. Here also we are using AFNet, but we are directly using the lowest bit here. But here, I mean, anyway, it's moving to the register, but it's getting pushed to a stack. But we have to fill that stack's padding. Internally, anyway, it is going to do the padding for us. But here we have to keep the space for that when you are pushing the values. So if you want if you want to get more into this, why we are doing this push word here, you just try to refer the socket addr_in, and if you go deeper into that one, why, then you will come to know why we do this here. So here I'm commenting it is f_inet, right? It's f_inet. So now we have the IP, AFNet, port, and IP into the stack. Now before, when we try to make the call, actual call, what we can do, and again I'm just going to make the syscall here. So before moving forward to the syscall, what we can do is we can the first parameter already filled here. RDA already have the socket file descriptor. So the second parameter is going to be the RSI. RSI is going to have what should be RSI going to have is the stack pointer. So now we have the stack pointer and RSI. So the second parameter for this one, first one is already done, the second one we got. Now the third one is the third parameter. What we have to do fill is going to be in the RDX. So before moving setting up the RDX, I strongly recommend to do a XOR on RDX. So move RDX with the length of the structure, that is 16. So now we have everything in place. So just make the syscall. What was the syscall number? Syscall number for this one, I think we already did. 42 is the syscall number for this one. So now we do the connect syscall connect. Now we have created a socket syscall instruction set and the connect instruction set, and we created the socket address in the stack, and we pointed the stack pointer to a second parameter, and the first parameter is the socket file descriptor, and then the third parameter was instead of the RDX here, what I say, we just need, what is the lowest bit for this one? DI, I think. DX was DL. You can make use of this one for optimizing the code. Yeah, we try with the different options with the shellcode. So now the next thing is we have to call dupe2. What was the syscall number for dupe2? We have already checked that one. I think it was the dupe2 syscall number. Okay, we'll do it again. It's 33. So we have to when calling the dupe2, it's just the file descriptor and socket file descriptor and std in and outer values, so it is easy. Here just we did here. Okay, now make the other syscall. Before making that syscall, I'm just clearing the RX and move L with 33 and move the next one is we already have the RDA with this file descriptor. So the next parameter, the second parameter for the function dupe is going to be in RSI. So I'm just clearing the RSI here, and then I'm moving RSI with 0 for the first call. This is for std in. So we are redirecting the stdin to the socket file descriptor here. So that's what we need for our shellcode, in fact. And this is not going to be, we are just converting the XAT instruction set here, but this is not going to be an optimized way. But we try to extract the shellcode first, then we think about the optimization. If I had time, we will do. Otherwise, I think it's going to be a long video. Let me check. Again, I did XOR RSI. Okay, instead of okay, now we need actually, oh no, here we don't need this one. We already did XORing here. So now we have RSI has 0. Why? Because stdin, like the syscall here, and now 33 again, XOR ASI, not XOR actually, we have to increment it, right? The first one is 0, second one is 1, and third one is 2. So there is another instruction called inc RSI. Why? There is no need of this one. We already did XORing, that was a mistake from my side. So now we have the second syscall with RSI. This is going to be std out, because this is 1 now. We are incremented the RSI with 1, then do the syscall, then again do the same syscall. Why? Because we need 3 here. This is for error. So we did the syscall 3 times. Now we know what should be doing. I mean, like, now we have done the socket call, the connect syscall, and the dupe 2 for 3 times by redirecting the standard in, out, and error. Then the next thing we need is the actual instruction for spawning the shell. Actually, see here. So here, so for this one, I'm going to make use of our same instruction set. Let us see how it works. So if everything goes well, this should be giving a shell to, just like this one, shell back to the attacker by the IP that mentioned here. This is IP, this is a port, and yeah, let us see. Maybe we may need to work more on this one, but let us see how it works in this one. So go to this, and what is the name of this one? Shellcode. Oh no, Shellcode. Oh, doesn't have any error. I'm saying rev shell for easier. So let us check rev shell exe. Let's create a listener here. nc-lvp 4444, and let us run this one. Rev shell exe. It works perfectly well. Like, if you see, we got a working shell. So it works. Now the next challenge for us is creating the shellcode for this one. First we check the shellcode in this one. Oh my god. Oh yeah, we did well on this one. There is no null bytes in this shellcode. I don't see anything, and I think we can make use of, yeah, anyway, this part we already tested, so you don't need to worry about that. I was worried about this shellcode part, but I think this is fine. So we are going to make use of this shellcode. We will try this shellcode inside our wrapper, and then we check. I don't know, sometimes it may not work, sometimes it works. Let us go to our run C and try this shellcode here. Let us run gcc-o rev c shell sm. Let me delete the rev shell. What is it? ls. Yeah, I already created a rev c shell. Remove rev c shell. Then gcc-o rev wrap shell. Run this. Yeah, it is showing no error here. Let me run lvp 4444. So let's run our shellcode. Wrapper. Oh yeah, see, even though it's 118 bytes, if you try to try again, you may have a chance to reduce the number of bytes. Maybe we may not need or some of the XORing options, and we will get more options to optimize the code. But now it is 118 bytes, and inside 118 bytes we successfully developed a shellcode from the assembly, and we tried it inside a wrapper, and it is working perfectly. This shellcode is working perfectly for us. So yeah, that's for this video. This is what I planned for. Basically, I just wanted to show, here we are starting a new series for malware development. So before going deeper into malware development, it's always good to know about the assembly programming. And this is the first part of this, and definitely it's going to be continued with the Windows options. Now we have explored a bit on normal 64-bit options, and there are so many other constraints you need to be aware of, like NX and ASLR stuff, but we'll be diving deeper into those things in upcoming videos. And this is a beginning for assembly programming with shell coding. I try to do the same thing for Windows also. Let us learn together. And that's it for this video. And if you like it, the content, or if you are interested in more shell coding and malware stuff, stay tuned. I'll be coming out more videos soon.